We're talking about the solubility product constant, or the K, for insoluble salts. You should already be able to identify salts as basic or acidic, and write mass accident expressions, even to find the pH of an acidic or basic salt. But by the end of the video, you're going to be able to calculate the concentration of the ions in an insoluble salt. So salt that would normally not dissolve to the naked eye, there are ions dissolved in there, and then we want to know how many. So let's review what happens when a solute is added to water. If your anion and your cation are both strong particles, like in salt water, the Na is from strong sodium hydroxide and the chlorine is from strong hydrochloric acid, the salt just ionizes and stays ions. Similarly, if you have a strong acid alone, HBr, it just ionizes into H3O+ or H+ and bromide ions. Or if you have just a strong base, it ionizes fully. Notice they all have single-headed arrows and they're ionizing and staying ions. In all these reactions, the ions stay in the solution and they can conduct electricity. They are good electrolytes, that's why we say that they're strong. But what happens when we add an ion that's weak to the water? So if, like in the example of KNO2, the potassium is a strong ion, it is a spectator, it will stay in the solution. The nitrite ion is not strong, it has too few oxygens, and so in that case, the NO2 rehydrolyzes with water, takes back the hydrogen, and forms hydroxide ions, which is why we called it basic. Or in that case, we could do the same thing with if we had magnesium chloride, this time the magnesium being an ion that is not strong enough to stay in the solution. So the magnesium ion might take back its hydroxides and form hydronium, which is why we call that an acidic salt. So in these conditions where an ion is weak, the ion reacts with water and takes back its hydrogen or hydroxide. We learned that in the last video. But in the case when both of them are both weak, in the case where copper fluoride forms copper ions and fluoride ions, and both of those ions want to grab back H's and OH's, you create this equilibrium condition, which shouldn't have a single header arrow, it would have a double header arrow, and we wonder if it's going to form copper and fluoride, or it's going to go back to copper fluoride, right? Stuck together, or ions, and it kind of goes back between the two. They barely dissolve, it mostly stays CuF. Neither ion wants to dissolve, so there's no driving force to make this solute dissolve. Nevertheless, some might. So if you see a precipitate, like this one might have been like a lead precipitate or a calcium precipitate or something like that, if they're forming a precipitate and it's not dissolving the solution, that doesn't mean there aren't some few number of ions in the water. So this is our second to last K, thankfully. We're talking about something called the solubility product, or how well it dissolves, which is not very well at all. And solubility is generally expressed as the mass of the solutes in a liter solution, grams per liter. If you remember in our Regents reference tables from last year, we used to see solubility tables, and it was how much dissolved in the water. Molar solubility is actually more useful in our K expressions. They're going to be molarities, just like all other Ks. That's why we use the brackets. And so if you're using a Ksp, you need to use molarity units, even though in the lab you probably use solubility. You said this much dissolved in the water, and you'll have to fix that for moles. It's really just a mole calculation, so let's do that first. If they say the solubility in a lab was 0.67 grams for every liter, that is not a very good solubility. You have an entire liter, that's like half a big thing of soda, and you can only get less than a gram to dissolve. So we can already see calcium sulfate's pretty insoluble. You're getting some to dissolve, but mostly not. We want to know what its molar solubility is in order to calculate a K later. So what we would just do is 0.67 grams over liters, and we would change just the grams portion to moles. So we would divide by calcium sulfate's molar mass on the reference table, calcium plus 4 O's, which is 136.14, and say that's a mole. Now what you'll have is moles per liter instead of grams per liter, since the grams cancel. And now this tells you the molarity that can go into our ice boxes and our Ks. Similarly, sometimes they give you a molar solubility because you got it from an ice box or a K, but you want to know what that really means in a lab, gram solubility, right? So we should be able to go back and forth between the two. So what I would do is take the 1.8 times 10 to the minus 7th moles per liter, that's what molar means, and change just the moles part. So moles goes down, the grams that I got was from copper plus oxygen plus hydrogen plus oxygen plus hydrogen, right? And it's 97.55, and I multiply across, and now I can see that that means a very small portion, 1.8 times 10 to the minus 5 grams, dissolved in that same big liter solution. So that's even less soluble. If you're going to compare your solubility of two substances, make sure you're comparing the same units. So either compare their molarities, which in this case it's 4.9 times 10 to the minus 3 versus 1.8 times 10 to the minus 7. In that case, copper hydroxide is less soluble. Or check their solubilities, grams. So you can again see 0.67 versus 1.8 times 10 to the minus 5. Still, copper hydroxide hydroxide is less soluble. But you don't want to compare molarities to grams because they're not the same unit. Okay, once you're able to know which unit you're in, we should be able to write our K expression. So if you're looking at an equilibrium of barium sulfate, which is not particularly soluble, it forms barium ions and sulfate ions, but it might go back and forth between the two. If we wrote our K expression, it would be barium ions times sulfate ions, and then you might want to divide by barium sulfate because that's usually how we write Ks, like products over reactants. But in this case, the reactant is a solid. So if the reactant is a solid, we don't write solids or pure liquids, like water, in our Ksp. So in that case, the Ksp is just the ions times each other. Again, no waters and no solids in your solubility product. So now we're just going to talk about how to write our Ksp expressions. What I would generally do, and you should write this green box down, is for Ksps, still products or reactants raised to their powers, but notice what I did was, if you want to circumvent writing your ice boxes, you'll take the power that it's at, x, and also keep it as its coefficient. So that's a little trick. You don't have to write it this way, but it will help you skip the icebox if you prefer. And I'll show why that works. So if I was going to write it for MgF2, I'd say that Ksp is Mg ions times 2 fluoride ions, because there's a 2 here, squared. Now if on the test you wrote Mg plus 2 times fluoride squared and no 2 here, that's okay. The squared definitely has to be there. Let's write it again for silver carbonate. So that would be Ksp equals 2 silvers squared times a carbonate ion. And notice there's only 1, so I only have it to the first power. Again, if you didn't write this coefficient of 2 here, that would be okay. And one more time, I would write 3 calcium ions cubed, because the 3 should match, times 2 phosphate ions squared, because those 2 should match. Again, if you don't have the coefficients there, that's okay, but the 3 and the 2 should be there, right? And you'll see why I'm putting these in a little bit. So now we're going to kind of put it all together. We're going to use the molar solubility stuff we just talked about before, moles per liter, and the Ksps, and we're going to write out our equation. So if we know that the molar solubility is 1.8 times 10 to the minus 5 moles per liter, and we want the Ksp of copper hydroxide, what we do is say copper hydroxide will ionize into copper ions and 2 hydroxide ions. The Ksp, initially you'll have copper hydroxide and no ions. It will shift to the right. Notice this is not like an acid or a base, and that when you take from your unknown amount and you add to the side, notice that there's 2 hydroxides. So that means you have to have 2x there. And when you get equilibrium, you're going to have unknown amount, because they didn't tell me how much, minus x equals x and 2x, right? Now the reason I wrote unknown, again, they didn't tell me what molarity I'm starting with, is saying this is how much dissolves. So that's our x, like our x values. It's not our starting. And it doesn't matter actually how much I start with, because that is a solid. So we want to be writing that on our Ksp anyway. Like if we write our Ksp, it's just copper ions times hydroxide ions squared. So notice that there's no copper hydroxide in the Ksp. So that's why it didn't really matter, that part of the ice. And so if you wrote your ice box out, you would know that you would have a 2x. It would be x and then 2x, right? Squared. But if you wanted to do the shortcut, what I was saying before, is that having the 2 there, you can actually skip the ice box, because if you know that for Ksps we keep the coefficient in front, it's kind of doing the work for you. So now what I'm going to do is take that's the molar solubility, the molarity, which is the bracket, and I'm going to plug that into each time I see an ion. So the Ksp is an ion here for copper and 2 ions here squared. You can either do 1.8 times 10 to the minus 5 times 2 times 1.8 times 10 to the minus 5 squared, or some people choose to just like kind of say there's an x here and an x here, so x times 2x squared is 4x cubed, and then they only plug it in once. Let me say that one more time. So you can either plug in 1.8 times 10 to the minus 5 in for each ion. So you would do 1.8 times 10 to the minus 5, and then 3.6 times 10 to the minus 6, or minus 4, right? That would go here twice as much, squared. And you'll get the same answer as what I'm doing. What I'm doing is choosing to only plug it in once. I'm saying copper is an ion, and there are 2 hydroxides, 2x's squared. 2x squared is 4x squared, right? And then 4x squared times another x is 4x cubed. And then that way I can plug it in just once. There's a little typo here. I think that should say minus 5. So in that case, when I plug in my calculator, either way you plug it in, you're going to get a Ksp value of 2.3 times 10 to the minus 20th. Take a moment to think about what that means. If your K is really small, that means it doesn't happen very often. And in this case, what it's saying is it doesn't form a lot of ions, right? It's mostly stays copper hydroxide. It's mostly reactant favored, and that's why you're seeing a lot of solid, because that's a solid, right? And you're seeing some solution, because that's why the solution is not clear. It's like light blue, because some of the ions are in there, but in a very, very small molarity, 1.8 times 10 to the minus 5. Let's try that again with a new substance. So again, the Ksp of calcium sulfate, the molar solubility is 4.9 times 10 to the minus 3. Again, that's the molarity that's going in your Ksps. So it's not the molarity you started with. So we're going to say calcium sulfate forms calcium ions and sulfate ions. I don't know how much I have, but I know I don't have ions initially. And as I change minus x plus x plus x, at equilibrium I'll have some amount minus x, x, and x. Again, this amount doesn't matter because it's a solid. And if I wrote my Ksp, I wouldn't have written it with that solid in it anyway. So it would just be Ksp equals calcium and sodium sulfate. Because they are both x, I can plug x's in there or get x squared. Another way I knew that without showing all the initial black work was because there was only one calcium ion and one sulfate ion in the calcium sulfate. I knew they were both x, and then I could just skip right to the blue part. And now what I'm going to do is put the 4.9 times 10 to the minus 3 in for my x, and so just square it. And my final answer is 2.4 times 10 to the minus 5. So what this is saying is this is also not very soluble. 2.4 times 10 to the minus 5 is a small Ksp. But comparing it to the previous example, when we had times 10 to the minus 20, this is much more soluble, right? So we can actually compare substances and say, if we had the same amount, would one dissolve more than another? And so we actually use calcium sulfate is a way of like creating like groundstone for plants and stuff, and gypsum. The next one says, calculate the molar solubility of a compound of XY3 if the Ksp is 1.5 times 10 to the minus 2. Even though we don't know what the substance is or how much we have, we can still figure out how much is going to dissolve or precipitate out, as you can see in the picture. But this one's a little bit backwards. The Ksp is given. So we're going to do this a little bit slightly differently, but it starts the same. XY3 will break into X ions. I can tell that they're probably like plus 3 because there are 3 Ys here, and each Y might be minus 1. It wouldn't be the end of the day if you wrote something like if 3 Ys are minus 2 and X is plus 6. But I mean, what are the chances, right, that something is plus 6? Anyway, so just use your reasoning for charges here. And that means that whatever I had on a known amount is going to ionize. It's going to shift to the right, so we're going to take away from what I have and add in 1x here because there's 1x, and 3x's here because there's 3 y's. And at equilibrium, you have an unknown minus x, 0 plus x is x, 0 plus 3x is 3x. Again, this left side doesn't matter because it's a solid, and we're seeing how well the solid dissolves, so it's out. That means that if I wrote my Ksp, it's going to be x times 3x cubed because it needs to always be raised to the power it has. However, I could have skipped all the black part if I knew that Ksp is always equal to the first ion and how many there are. There's only one. And that the second ion, how many there are to its power, so 3 and 3. That helps you skip this whole section, but only if you remember to keep the coefficient there. What I could do is either choose to write 1.5 times 10 to the minus 2 on the left and then solve for each x, but usually I just condense it. So I'm going to put 3 times 3 times 3 is 27, and then that means I have 4 x's, 27 to x to the 4th, because it's a little easier to work with if I have everything condensed. Then plug the Ksp in. So you see how this one's a little separately different? It didn't give me the molar solubility. It wants the molar solubility. It gave me the Ksp. So remember, if it's molarity that they're giving you, that goes in the bracket. If it doesn't have a unit, that goes in the Ksp. Then I'm just going to divide by 27, and then do the 1/4 power, right? It's not even a cube, it's a quarter power. And that's going to give me an x value of 0.15. This is actually the most soluble of the 3 that we've done so far. It dissolves at 0.15 molar, which is actually pretty decent, and its Ksp was one of the largest. And that's why you're seeing the solution is more opaque, right? You actually do have ions in there. At this point, you should be able to calculate concentration of ions in an insoluble salt.